All right, welcome in. We are moving on to chapter 2 in our textbook. This is Chemistry 202, and we are beginning our journey into coordination chemistry. In the past, maybe we spent some time, maybe just previously thinking about organic chemistry and carbon-based molecules. Well, now we're going to switch gears and start to think about inorganic chemistry, chemicals and molecules that contain metals. We'll start in this video by looking at the trends and properties for our transition metals. And in the subsequent videos, we'll move on to coordination chemistry and crystal field theory. All right, we do want to investigate and learn about these metallic containing compounds. They do show up all the time in our lives. These are useful for building materials. These are useful for modern devices in electronics. They're used all the time in biomolecules. The functional centers of many biomolecules contain these metals, and it's important to keep track of metals that show up in our environment, whether these are good and helpful for useful minerals that we need to grow plants and ensure life can thrive, or perhaps dangerous and keep track of contaminants in our water, so on and so forth. The metals on the periodic table can either be main group metals, groups 1 through 2 and 13 through 16, or we can have transition metals, groups 3 through 12. Or even further down on the periodic table, underneath everything, we can look at maybe inner transition metals. Okay, in the past, maybe we've learned already a little bit about some of the main group metals, but probably the transition metals we've focused less on in previous chemistry courses, which is why, all right, it's time for us to do that now. Transition metals here, we can have a definition. These are going to be metals that form or have partially filled d orbitals. We're going to look for electron configurations that have partially filled d orbitals. We're looking at the periodic table. The transition metals will start here with Sc, scandium. Call this the first transition series, elements 21 out to about 29. Notably here, zinc will have an electron configuration of 3d10, which would be considered a completely filled d orbital, which would make zinc, in some senses of the word, not a transition metal. We can say the second transition series will be yttrium through about silver, elements 39 through 47. The third transition series will be the elements that contain partially filled d orbitals down here in period 6. Notably, the numbering system, 57, 72, 73, we have our lanthanides that exist. We write them below the periodic table. Those elements fit in between La and HF. We're not going to be thinking about them right now while talking about the transition metals. We want to just think about the ones which, have those partially filled d orbitals. All right, so these are the transition metals that we'll spend some time at the trends and properties for. Group them based on what series that they're part of. And we want to be thinking about the trends and the properties. They'll have a wide variety of properties, maybe some more confusing trends to keep track of, as opposed to the main group elements where things are more predictable. All right, we have a quick practice question here, quick review question. Can we write down our electron configuration for some of these elements? Feel free to try these questions and see if you can get the answers. You can look up the answers on our favorite website, ptable.com. For us, we'll move on and start thinking about another practice question. For each of these properties, how does the trend change across a period down a group? Well, hopefully we remember this from our previous courses. All right, to understand our periodic trends, one of our most helpful tools is going to be effective nuclear charge. Effective nuclear charge. This is the charge in our nucleus accounting for any electrons that might also be around our atom. So in our atom, our nucleus contains those protons, those positive charges. Surrounding the nucleus is our electron cloud. We're thinking about the outermost electron. It will see the nucleus and be attracted to it. It will also see that electron cloud and be repelled from those other electrons, purely based on electrostatic effects. So if we're thinking about a given electron in our atom, the positive charge it feels from the nucleus is going to be slightly less than the number of protons. We can have an equation here. The effective nuclear charge, the charge that our outermost electron feels, is equal to the number of protons that exist in that nucleus, but subtracting some amount of shielding, which we can label as S. There are a number of ways to calculate what this value for the shielding might be, to estimate what it might be, or we can even look up and see what the literature values might be for any given atom, how much shielding should exist. If you want a very simple approach, we can say that the simple approach is our shielding is equal to the number of core electrons. This approach will give us, well, an okay answer. It's not perfect. It's actually not that great, but it's close enough to give us most of the trends. If you want a more complex approach, on the next slide, we'll look at what's known as Slater's rules to estimate the shielding and the effectiveness. Or, like I said, if you want to have more precise values, we can look up values. All right, a little bit of bonus information here. If we want a precise way for estimating the effective nuclear charge, better than just our quote-unquote simple approach on the previous slide, well, Slater's rules gives us a method for doing this. We can account for the fact that S and P orbitals are better shields than D orbitals. And we can account for the fact that F orbitals are especially poor at shielding. We can say that electrons in the same group don't shield very well. Electrons that are closer to the nucleus shield much better. And we can end up with an estimate for the shielding value, which is, well, better than our simple approach. You can see here, I'm telling you, you don't need to memorize this. We'll maybe practice it a little bit, but I won't be putting this on any exams for you in my course. Although it's nice to know that these rules exist and that there are ways to estimate our effective nuclear charge to a higher amount of precision. All right, now that we've introduced our effective nuclear charge, refreshed our memories on our periodic trends, let's start to look at the trends for our transition metals. So first things first, let's look at our atomic radii. So in general, our atomic radii decreases across a period. Our atomic radii increase when we go down a group based on effective nuclear charge. As we go across a period, the effective nuclear charge gets bigger and our atom gets smaller. When we're going down a group, we are increasing the principal quantum number. When we increase the principal quantum number, our orbitals get bigger and higher energy. We have just larger orbitals as we go down a group. For our transition metals, okay, our trend is going to be, well, not quite as consistent. We can see that on this graph. This graph shows the position on the periodic table within the D block element. and it shows the atomic radius on that y-axis. So our first row in blue here, where the cursor is, we can see our first transition metal series. Okay, as we go to the right, our atomic radius does decrease. There's a few deviations. The atomic radius is not that different as we get towards the middle of the D block elements, and there's some more deviations at the end. But in general, okay, as we go to the right, the atomic radius tends to mostly decrease. We see that same general trend for our second row, starting with yttrium, and our third row, starting with lanthanum. We can see, okay, in general, the atomic radius gets smaller going towards the right. So across the period, in general, the same trend that we expect, with a few deviations towards the end of the block. When we go down the group, we can look at the first row compared to the second row compared to the third row. We expect our atoms to get bigger as we go further down the periodic table. Between our first row and our second and third, we do see that increase. That first series of transition metals is smaller than the two that are below it on the periodic table. However, we have an exception, and we call this the Lanthanide contraction. Between the second and the third row on the periodic table, the second series and the third series for our transition metals, they have very similar atomic radii. This is because, well, we have a lanthanide contraction. We start to have F electrons for our third row in that D block. Those F electrons are not going to do a good job at shielding. And so we have more protons for these third row elements, but the electrons are not holding up their end of the bargain. They're not doing as good of a job of shielding. And so the effective nuclear charge for the lanthanide series is much bigger than it is for the rows above it. Our result here, when we get to period 5 and 6 on the periodic table, the atomic radii are similar to the second row elements. All right, the second trend that we will look at is first ionization energy. All right, let's recall. In general, when we go to the right on the periodic table, the ionization energy is going to increase. The effective nuclear charge increases. It is harder to remove an electron. This is going to require more energy. The ionization energy increases. This will have the same trend as our effective nuclear charge. When we go down a group, our electrons are in orbitals with a higher principal quantum number. Those electrons are in a higher energy state. They are further from the nucleus. They are going to be, in general, easier to remove. Our ionization energy should decrease as we go down a group. That is the trend when we have predictable elements, main group elements. Let's look at what happens for our transition metals. For our transition metals, we can see again on our graph. Here are those transition metal series. The first row in blue, we have the second row in red. So moving towards the right, going across a period, we expect the ionization energy to increase because we have a larger effective nuclear charge. And that is true. The values here on our graph increase as we go towards the right. Higher effective nuclear charge leads to a higher ionization energy. When we're starting to look at going down a group for our transition metals, well, going down a group, we see very little change between the first row and the second row. Period 4 and period 5 on the periodic table, there's not that much of a change. Turns out the ionization energies are relatively similar for period 4 and period 5. Once we get to the lanthanide row, that third row on the periodic table, we get to, we call this period 6. Well, when we jump up to period 6, we have an increase in ionization energy. This is going to be, well, maybe that opposite of the lanthanide contraction trend we saw for atomic radius, but it's because of the exact same ideas. When we get to elements that contain F electrons, well, those F electrons are not going to do any good at shielding. And so the effective nuclear charge for here period 6, what we call the third row on this graph, the effective nuclear charge is going to be larger than you might initially expect, which leads to a higher ionization. All right, one last periodic trend for our, well, at least graph view of these trends. We can start to think about electronegativity. So for the main group elements, our most electronegative atom is fluorine. Moving to the right across the periodic table increases the electronegativity. Moving down the periodic table decreases the electronegativity. Electronegativity increases as you move closer to fluorine. Okay, for our transition metals, we're going to have a slightly different trend. The electronegativity for periods 5 and 6 ends up being much higher than it is for period 4, or at least a little bit higher than it is for period 4. The lanthanide contraction here is going to be a factor. Lanthanide contraction will hold our electrons a little bit tighter. They're going to behave maybe slightly contrary to the normal trend. That's not the only thing going on here. There's more to it than that, and in fact, things that are beyond the scope of this course. But at some point, you need to account for, well, very, very large nuclei with lots of electrons pulled very closely to it. You start to have to deal with relativistic effects with these very, very large atoms. So again, not something that we will have to deal with in our course. There's a lot going on here, but the lanthanide contraction does play at least some factor in bucking the trend for electronegativity. The result here is that, okay, fluorine is the most electronegative atom, and the trend for our main group elements is that the closer to fluorine you get, the more electronegative you get. Within the transition metals, actually gold is going to be the most electronegative. We have gold as the most electronegative, this point up on our graph at the top right. As you go to the right and you go lower within the D block elements, you increase the electronegativity. All right, we can also look at some trends in the oxidation states that are available to our transition metals. Transition metals tend to, 1, lose their s electrons, and then 2, start to lose some d electrons. When we are removing valence electrons from these atoms, we actually start by removing the s electrons and then remove some d electrons. When you're starting to form cations for these metals, forming different oxidation states for these metals, you are not going to see oxidation states that exceed the number of valence electrons. We're not going to start removing core electrons when forming cations, forming these oxidation states. As a result, as you go to the right on the periodic table, we have more valence electrons. We have more options for oxidation states that might form. If you're looking at scandium, things in group 3, we have 3 valence electrons. Maybe we can form an oxidation state of 3+. You won't see an oxidation state of 4+, because that would require removing a core electron, which requires way too much energy. Titanium, however, has 4 valence electrons. You can remove all 4 of those valence electrons, get to an oxidation state of 4+. Or perhaps you'll see something where you remove only 3 valence electrons. That's a fine option as well. Titanium is commonly +3 or +4, depending on the context. Moving one spot over, vanadium has 5 valence electrons. You can see oxidation states as high as +5, but there are options. You might also see +2, +3, +4. Right, we can see this pattern continue. You can get to higher oxidation states the more valence electrons you have, but it doesn't have to be removing all the valence electrons. You could also stop at removing just the 2 or maybe 3 or so on and so forth. Removing 2 is common. That would correspond to removing only the s electrons. Other oxidation states are possible. In fact, more are being forced and discovered as we go along. In 2014, iridium +9 was synthesized. So even beyond the ones listed on this chart, others might be possible, but they're going to be harder to get. Another trend as we go down the periodic table. This is our first series in the D block elements. As we go down the periodic table, our atoms are bigger. We're going to be able to remove those electrons more often. We're going to have more oxidation states available for our larger and larger atoms. All right, so we've discussed our atomic radius. We've discussed our ionization energy, discussed our electronegativity, and we've discussed our oxidation states for these transition metals. We would like to know the general trend for all of these in terms of what's the general trend for main group elements, what differences do we expect for our transition metals, and what are the explanations for those bucks in the trend. Usually those F block electrons causing some weird phenomena. We have a practice question here. Feel free to pause the video and see if we can answer it. If you have any questions, I'd be happy to answer. I look forward to seeing you again soon in the next video. And thank you and have a great day.